Welcome to the Introduction to Magnetism. Today, we will explore the fascinating world of magnetic fields and materials. Magnetism has a rich history, starting with the discovery of lodestones. Over centuries, scientists like William Gilbert and Hans Christian Ørsted have significantly contributed to our understanding of magnetic properties. The 19th and 20th centuries saw groundbreaking discoveries by scientists like Michael Faraday and Pierre Curie, who expanded our knowledge of electromagnetism and magnetic materials. William Gilbert and Hans Christian Ørsted are considered the two pillars of magnetism for their pioneering work in the field. Magnetic materials can be classified into two main categories: temporary magnets and permanent magnets. The periodic table highlights elements with different magnetic properties, including antiferromagnetic, diamagnetic, ferromagnetic, and paramagnetic materials. Iron, cobalt, and nickel are common magnetic materials, each with unique atomic structures and properties. Magnetic moments and magnetic fields are fundamental concepts in understanding magnetism. Electricity and magnetism are closely related. The shape of the magnetic field around a current-carrying wire and solenoid demonstrates this relationship. Magnetic fields are generated by the movement of electric charges, creating magnetic dipoles. A magnetic dipole has field lines running from the North Pole to the South Pole, indicating the direction of magnetic force. A bar magnet behaves like a magnetic dipole, with field lines showing attraction and repulsion between poles. Magnetic dipoles are often represented schematically as arrows, with the head indicating the North Pole. Magnetic flux density, or B, measures the strength of the magnetic field passing through an area. Higher flux density means stronger magnetic forces. A magnetic dipole in a field experiences a torque, which depends on the magnetic field strength and the dipole moment. A magnetic dipole aligns with the magnetic field, showing the interaction between the dipole and the field lines. Flux density within a material is determined by the geometry and current in the solenoid, as well as the magnetic properties of the material. In the absence of material in the solenoid, the magnetic flux density is determined solely by the magnetic field strength. Magnetic susceptibility measures how much a material will become magnetized in an applied magnetic field. The response of magnetization to an applied magnetic field varies with the type of material, temperature, and magnetic history. Vibrating sample magnetometer instruments are essential for calibrating the magnetization values of ferromagnetic materials. The mass susceptibility, volume susceptibility, and density of the material are key parameters in this process. Susceptibility and permeability are fundamental properties in magnetism. They help us understand the relationship between magnetization and field intensity, as well as the total flux density. For certain materials, low field magnetic susceptibility is inversely proportional to temperature, a principle known as Curie's law. Magnetic materials can be classified into diamagnetic, paramagnetic, and ferromagnetic categories based on their magnetic properties. Diamagnetic materials exhibit a very weak negative response to magnetic fields, resulting in small negative magnetic susceptibility. Paramagnetic materials align with magnetic fields, showing a positive response and increasing magnetization with the applied field. Ferromagnetic materials exhibit strong alignment with magnetic fields, resulting in high magnetization even after the external field is removed. Hysteresis loops illustrate the difference in magnetic properties between soft and hard magnetic materials, showing how they retain magnetization. Ferromagnetic materials form magnetic domains, each magnetized in different directions to minimize energy due to stray fields. Natural magnetic materials have randomly oriented magnetic domains, and the domain size is determined by the balance between magnetostatic energy and domain wall energy. Magnetic domain walls have a typical thickness of about 100 nanometers, playing a crucial role in the behavior of magnetic materials. The magnetization process involves aligning domains with the applied magnetic field, and the hysteresis loop shows the history-dependent nature of this process. Thermal energy can overcome exchange interactions in ferromagnetic materials, with the Curie temperature indicating the strength of these interactions. In antiferromagnetic materials, exchange interactions favor antiparallel alignment of atomic magnetic moments, resulting in zero remnant magnetization. Ferromagnetic materials have different sized moments on each sublattice, leading to net magnetization despite antiferromagnetic exchange interactions. The response of a material to a magnetic field is called magnetic induction, and the relationship between B and H is a key property of the material. Different types of magnetism exhibit varying levels of susceptibility, from diamagnetism to ferromagnetism. Magnetism in materials originates from the movement of electric charges, with the spin of electrons playing a significant role. Units, conversions, and values for magnetic materials are essential for accurate measurements and understanding of magnetic properties. Thank you for your attention and interest in the fascinating world of magnetism.